let's get started on the thing because we got a lot of stuff to go through today. So chapter 23 is where we're starting. We're going to finish chapter 23 definitely, and I want to finish chapter 24. If we finish chapter 23 and chapter 24, that would be fantastic, and we'll see if we can do that. So let's just jump right into it. As always, my notes are available in homework help, and that's what I will be making reference to. In fact, I should actually have that open. Just open that up quickly. And then, yeah, that's it. Any questions before we start on these questions? Any questions before we start on the problems?
Yeah, so just these problems, are they taken from the tutorials or they're just textbook questions?
Textbooks. They're just textbook questions. They're the
Okay.
suggested problems in the textbook. Sorry if you hear
Right.
a siren in the background, which will pass.
Not good.
Whoops. Knocked my light. Okay. Any questions? Another question before I go, or no? Okay. I think we're good. So, we're...
Is it questions, or how many questions did you say is going to be 16? Or 20?
How many?
Or what was
What's the question? Sorry? How many questions are in 23?
questions on the exam? Is that 23?
I can't hear what you're saying. What was
There's
it?
20 exam.
How
There's
many
20
questions
questions on the
It's
exam.
gonna be 20
How many questions on the exam? I think there's 20. Yeah. Okay. Okay, so question 11, let's start here. A flat surface of that area is rotated in a uniform electric field of that magnitude. Determine the electric flux through this area when the electric field is perpendicular to the surface, when the electric field is parallel to the surface. Okay, so the electric flux is defined as the electric flux is the electric field magnitude vector, or electric field vector, times the normal vector of the surface. Just through a surface, it's this, right? Through a flat surface. Someone's got their mic on. Abdul, we got your mic. There you go, thank you. Okay, so let's see here. It's rotated in a uniform electric field, so it's only going in one direction here. So let's just say it's going in this direction. So the E vector is, well, it's just a vector like this, right? Okay, actually, you know what? A better way to do it is to say, well, it's a dot product of two vectors, so we just take the magnitude of this times the magnitude of the area vector times cosine of the angle between them, right? So the magnitude of the area vector is 3.2 meters squared. The magnitude of E is 6.2 times 10 to the 5. So we just have two situations where theta is different, right? So part A, theta, the angle between the two, the electric field is perpendicular to the surface. So that means that the surface is like this. I assume they mean the surface is like this, and the electric field is like this. Right? So that would be cosine of 90, which is 0. Right? I think so. Yes? Cosine of 90 is 0. So here theta equals 90 degrees. Cosine of 90 is 0. You got my calculator anyways. Not that I have to do that, but yeah. So cosine of 90, and then for part B, so this is 0. So we know that the answer for the flux is 0. Therefore, flux equals 0. And then for part B, when the electric field and the electric field is parallel to the surface, so that means
So
yeah.
I think I did the exactly same as you, but the answers are the opposite.
Opposite, yeah. So then I'm just misunderstanding the way that this phrasing. So the electric field is perpendicular to the surface. That means that
Yeah, so it's parallel to the vector.
area vector.
If it's
Yeah.
perpendicular. Yeah,
Okay,
I did
makes
the
sense.
same thing.
So that's the electric field going up. I'll do it with colors here too. This is the area vector going up. That's the electric field vector. So there, it's perpendicular. The electric field is perpendicular to the surface. That means theta is 0. Cosine of 0 is 1. So that means that the flux is just the magnitude of the electric field times the magnitude of the area vector times cosine of 0. So I'm getting squished there a little bit. So then that's just going to be 3.2 times 6.2 times 10 to the 5. And so we just get 3.2 times 10 to the 5, which is 1.984 times 10 to the 6. Whatever the units of that is. What are the units of flux? I forget now.
Newton meters squared per coulomb, I believe.
Okay, let me see if I have it in my notes here. Yeah. Although that does seem right. I don't think I even have it in my notes, surprisingly. Yeah, it would be.
I'm just thinking of the units of E and the units of A added together. So I don't know.
Yeah, that makes sense though, because it'd be Newton meters squared per coulomb. Is that what you said, or per coulomb?
I think E is newtons per coulomb, right? Or
It
is it?
says, this is up there. See, it says E
Yeah,
equals.
newtons per coulomb, and then add meters. It's in the question.
Yeah, Newton meters squared per coulomb. Yeah, okay, that makes sense. I'm just also looking at the units of like if we do Q in over epsilon naught. That's like the other definition of it, and it also matches, so that's fine. So yeah, Newton meters squared over coulombs, and that is the flux. Let's check our answers.
So like, why is this the answer for A?
Why is this the answer for A?
Yes.
Well, because the only difference between A and B is the angle that the two things are going
No,
together.
but isn't it for A is 0 and for B that's the answer for B?
No, A theta is 0. Theta is 0. The angle between them 0. So cosine of 0. So you see plugging into theta equals 0 here. It's cosine of 0, which is 1. So it's just E times A.
No, I'm confused. Okay, so for point A, isn't it perpendicular to the surface? So for A, the answer is 0.
What? Like, the flux is not 0. It's perpendicular. So the electric field is perpendicular to the surface. So that means that here's the surface. Here's the surface. The electric field is coming up straight from it.
Yeah, so it'd be E times A times cos of 90, which is 0.
The angle between A and this is not 90. This is 0. So the-
remember that the A vector is also perpendicular to the surface. So if they're both perpendicular, they should be in the same direction.
So theta is the angle between these two vectors.
So is A always perpendicular to the surface and E
Yeah.
depends?
E they give you. A is by definition the normal vector to the surface.
I don't remember seeing A, to be honest, in class.
Yeah. So that's what it is. It's the normal vector to the surface. It's the vector coming right out perpendicular from the surface. Right. So B has theta equals 90. Sorry, not 9, 90. So what that tells us is that the flux, I guess I'll use a proper flux, that's proper flux, is E, magnitude of E, times the magnitude of A, someone's got their mic on, cosine of 90, which is 0, thank you, which is 0. So it's 0 Newton meters squared per coulomb. So that's it for that one. Any questions? If there is, I'll happy to answer. Ooh, it's loud in my ears for some reason. Okay. So there's that. Let's take a look at the next one then. Number 12 is a non-uniform electric field is given by this expression where A, B, and C are constants. Determine the electric flux through a rectangular surface on the xy plane extending from 0 to W and from 0 to H. Okay. It's not too bad. So let's see what we're going to do. It's of course going to be algebraic. So again, the flux, the electric flux, through a flat surface is the electric field vector dotted with the area vector. The area vector is perpendicular to this plane, right? Perpendicular to the plane that's created here on the xy plane. Right. So is it A, Y, B, Z? Okay, I think I'll just entirely do this algebraically. I mean, I guess I can just do the magnitudes. I guess I could do that. What's the angle between them, though? How would I find the angle between them? Okay, well, we can write E is a little confused by why it's AY, because what is X, Y, and Z? They're
I think
wait,
the
would this
coordinate.
just be the Z component? Or the X, or the Z component? Because wouldn't the X component and the Y component be parallel to the plane? Like, those are both in the X and Y planes. So they
yeah.
wouldn't,
So you're saying
those components wouldn't be going through the surface, right?
I think that's what the angle between them part is happening. That's like why you say the angle between them. You do so.
Just a quick question.
Yeah.
In this definition, isn't Z in the J hat direction? So isn't that technically our Y? Just
This Z value?
yeah, it is in the J hat direction, right? So isn't it technically our Y, or do we consider it just a variable Z?
Yeah, I think we just consider. I'm a little confused too. Why is Y, Z, and X here, and in that order, and also why are they here? What? I think we just treat it like a variable because it's a variable. Yeah.
Yeah, I was just
So
gonna
this is
ask. I think.
Yeah, and ABC are constants.
Yeah.
A, B, C are
A,
constants.
So I think
Multiply.
we
A,
can
B, and C are
find a
constants.
normal to the area plane, like we have it as from 0 to W and from 0 to H.
Yeah.
Find the normal, and then we can do vector
Well, what would the normal
multiplication.
be? It's from. The normal is just K hat, isn't it?
Yeah, that would be the direction, but do you remember from linear algebra, like how to find it?
On an infinite plane, like on an, but this isn't. This is like a finite plane. So
Can we just not use the other definition for like cross product, where you do like, because you know there was like you had the cos definition where you could just do cos wherever
Cross
like
product
yeah, but
doesn't do anything in this yet. I think that's
I think
magnetism.
I think he means dot product, but with the dot
I forgot
product.
that. Wasn't there, like the other definition, wasn't there like one with like if you multiply each component or something? Wasn't there like some other definition when you had two matrices? You know what I mean?
Like the dot for the dot product definition of the dot product.
Yeah, like wasn't there like some other definition when like multiply each element of the matrices or something? So
Oh
can we not
yeah,
just do
the
something?
vectors of the vectors. Yeah. So
Yeah, so can we not just do that?
that's what I'm thinking here. So this would be B, Z, C, X. So we have the E vector like this, and I just have to find the A vector, and then I could dot them. But what's the A vector? It's
Your area vector has to be
I would
normal, and then
say
it also
I
has
would
to
say
have the
the
magnitude of the area, right?
I would say
Yeah.
the A vector.
So then
Oh.
would it just be like WH K in the K hat direction?
yeah.
No, I would say
that
the
seems right to me. Yeah. Right? Yeah.
I think the A vector might just be 0, 0, and then something in K, yeah, like that.
Yeah. This is what I think it is. 0, 0, WH. That's
Wait, how do you know it's WH?
because it has to have a magnitude that's the area of the surface, and the area the side lengths are W and H. It's a square at the origin. Well, it doesn't have to be a square, but it's a surface at the
Oh, yeah.
origin with side length.
I
W.
realized that they say x equals 0 to x equals W and y equals 0 to y. Is this supposed? Do they expect us to do integrals?
Yeah, that's what I
Because
was
that would be a
thinking too.
definite integral, wouldn't it? You take
Uh-huh.
like you have 0 and you have W for your x, and you have 0 and you have H for your y.
No, I think it's just
Well, what am I
supposed to be-
integrating? What am I what like? There's no.
Well, I would assume you would integrate. Oh, that's true. What would you be?
What am I integrating? I think this should work. Let me just try it. So the E dot A would be CXWH is what I got for that. So let's see if that's the answer. Probably not though. 12 is not in the book. So let's see.
Yeah, that's one thing I can think of because I think you just have to use the other formula, you know, the one without codes, you know?
Yeah. Let's see.
So dot product is the one we just multiply each element, right?
Yeah, dot product is the one where you just multiply each element. That's right. Yeah.
Okay, so that makes the most sense.
So this is
See, I'm confused because we have E in components, and usually that means that if we're looking for a net of anything, you would add up the magnitude of each component that's going. Like, how much
Yeah, but
of the stuff that's moving in the x direction is going through the plane? How much of the stuff that's moving in the y direction is going through the plane? How much
Yeah,
of
but
the
like 2 of
z
them are
direction-
0, if you notice. Like, because like for A, the first 2 elements are 0, that means
You know
if
what?
you want
Why
to-
are we asking these questions? Look, Slater. Where's Slater? Come
yeah.
on,
I have Slater
let's
open.
find the-
I have Slater open now. So the general expression for
Slater's
electric
answer is-
flux. Yeah.
Or what's Slater?
Yeah, Slater's answer is not that like not that complicated. They just slap them into an equation and that's
Yeah. Well, it says it. Okay. I'll put it on the screen. What's here? picture. So
It's just the way.
this is what Slater gives. So the general expression for the electric flux through a surface is this integral. It's just that it's a flat surface, so we usually don't have to use the integral. The expression for the electric field is that A, B, and C are constants. The rectangular surface XY plane extends from that to that, that to that. Therefore, the expression for the electric field reduces to that. Why that? Yeah, why that? There's no
So they just assume that there's no X component, apparently.
no Z component. Because
No, there's K hat and there's no Y. Oh yeah, you're right.
there's no J hat.
That's the thing. They put an X in the Z area and Y in the X area. And then
Yeah, it's
they
really
do something.
confusing.
Yeah, they do some integral like this. So they do an integral. Let's see what's happening here though. So they're saying electric flux is that where dA is the vector representing the infinitesimal area, which is h dx. dA is h dx. Okay, sure. And we have to integrate that from 0 to w. I would not think of this at all though. Like not at all. So I'm not really sure. Also, why do the a y I hat plus c x k hat time dotted with h dx k hat, and then all of a sudden, all the c a y goes away for some reason, and all.
So wait, it is literally just only the Z only the K hat component of the E field, and then we just integrate that for whatever reason.
I'm confused how you have to integrate in the first place. Like, didn't they say we don't integrate any force? But then they say that like
I don't know, but
Can you copy their picture?
Sure.
Like their qubit that they created.
Yeah.
Like I don't think they're gonna ask any of this in the exam. So
I'd say yes. Let's not spend more than 30 more seconds on this. Yes. So
this is what I say. You see, Y is in the Z direction, X in the Y direction, and Z is in the X direction. So Z is X, X is Y, and Y
yeah,
is
let's
Z.
just skip because I think they said that there's no integration and like that. There's no integration in this course. There's no point like doing
Wait,
questions.
hold on. What are we saying here about X is in the what was it? Can you say it again?
X is in the Y direction. So technically, if you just hypothetically just say X is Y, Y is Z, and Z is X. That's what
But why?
they put.
Why? But hold on. Why? Like
Because-
dx is in the x direction here.
Yeah, but technically, if we did that normally, this is the Y direction. This is the J hat. This way, right?
Which
According to the right hand rule. The X direction is the J hat.
is no. It would be the I hat.
No, the X direction is the J hat according to the right hand rule. If you did it.
If you did it like, because
Yeah.
it's the other way. Because you'd have.
Yeah, I think that's what they did. That's why it's confusing.
Alright,
Because they
let's
put
just
the variable.
drop this question, guys. I don't. Think we
Yeah.
should
Yeah,
spend-
the question is there's no integration at the exam. I know that.
please.
We'll talk about it more, if we have time at the end. Okay, number
Yeah,
15.
exam.
Number 15 is next.
The trick you talk about after the exam.
Okay, so let's see here. Four closed surfaces S1 through S4 together with these charges are sketched. Colored lines are the intersection of the surfaces with the page. Find the electric flux through each surface. Okay, not too hard. So electric flux through S4, start with that, is 0. The reason is because there's no charges inside S4. So 0. Okay, let's do S3. I don't know why I'm doing backwards, but you just take the net charge, right? A net charge, and then divide that by epsilon naught. So -2, -3, +1, so it's just -2 over epsilon naught. S2 is this surface, so that's just 0. And S1 is just going to be -1 over epsilon naught. And that's it. Do they actually want the numbers for this? Let's see, 15.
Epsilon naught is a constant.
Yeah, no, it's just a constant. So that's correct. 0, -2. Yep, that's it. So just look at what's in the surface. That's all it's saying here. What's in the surface? The net charge inside. Divide that by epsilon naught. We're using the fact that, phi is equal to, we said before, well, it's equal to the integral, but it's also equal to q inside over epsilon naught. And that's right. Okay, that's question 15. Question...
Sorry,
Yep.
could you just go over the equation I have for S3? It would be negative q plus q, right? So would you have negative q in the numerator?
S3 is this whole thing right like that, right? So that's going to be, these two will cancel. So you have negative 2.
Sorry, I was looking at the wrong circle.
Yeah,
Okay.
there you go.
Yeah, that
Good.
makes sense.
Okay. So then that is 15. So let's look at 19. Oh boy. Okay, let's see 19.
These questions get so easy if you actually have access to formulas.
Let's see. So a particle with charge Q is 5 nanocoulombs, microcoulombs, I always say nanocoulombs by accident, is located at the center of a cube of length L. In addition, 6 other identical charges having those charges are positioned symmetrically around Q as shown in the figure. Determine the electric flux through one face of the cube. Well, I'm quite certain to do this, you take the electric flux through the whole thing, and then since it's symmetrical, everything's symmetrical, you just divide it by the number of faces, right? Which is 6. If I remember the number of faces. Yeah, 6. Okay, good. So essentially...
Yeah, that's right.
That's right? Okay. So...
Springer did this question.
Yeah,
Yeah, we did
his
it for
lecture
Springer.
Yeah.
So I'll just do it quickly. It's going to be the charge. So it's going to be the flux through one face is going to be, sorry, the flux through one face is going to be the flux through the whole thing. So the flux total, or I'll say net, divided by 6. So it's going to be Q in over epsilon naught, or 6 epsilon naught, right? So what's the charge inside? Well, the charge inside is, I'll do it down here, is 5 times 10 to the negative 6, plus, and how many charges? 6 charges? Yeah. Plus, or I guess I'll minus 6 times 10 to the negative 6. Negative 6. Yep. Over. I guess I could have just taken the net charge. I didn't have to do all that, so it's, okay, whatever. Over 6 epsilon naught. So this is just negative 1 times 10 to the negative 6 over 6 epsilon naught. And then, is that how far they want us to go? I don't know if they want us to actually type in the, this was number 19. Yeah, it does actually want me to type it in. So epsilon naught is just a constant, which is approximately something. So let's see. Negative 1 times 10 to the negative 6 over 6 times epsilon naught, which is 8 point... Someone's got their mic on. Could you mute, please? Times 10 to the negative 12. Okay, so we have here negative 1 times 10 to the negative 6. 6 times 8 point... So epsilon naught is 8.8542 times 10 to the negative 12. So I got negative 18823. Negative 18823 Newton meters squared per coulomb. Yeah, that's right. That's correct. Okay. Any questions about this?
So I know you use the formula with Q in over epsilon 0 ever to find the charge, but like, why is it divided by 6? Like, I understand it's because of a 6 face, but I don't get like the idea behind it. Because
So
the
the-
charge,
Mhm.
because like the charges are not on the face that like come, like it doesn't really
Yeah.
matter the same object.
Well, it's just the thing is that the flux through an object, or the flux coming out of this object doesn't at all depend on the shape of the object, right? So we can just measure the flux that's coming out of this in general, right? And that's what this Q over epsilon naught is. That's going to be, well, it's not going to be the amount of the face, but it's going to be just the net flux in general coming out of it. The charge inside, the net charge inside, divided by this constant. But since we know the total amount coming out, we can also figure out the amount through each face because they're all symmetrical. They're all the same area, right? They all have the same area. So you
Yeah.
So you just divide it by 6.
Okay, now I get it. Because so you don't have to, like, as long as they're kind of part of the same object, it doesn't really matter where in the object they are.
As long as it's symmetrical, that's the important thing. Everything was symmetrical here, right? So it doesn't matter where. Everything was like, yeah, the net flux is the same through all the pieces.
Could we get a question where it's not symmetrical or not really?
No, you couldn't. You won't get it. It's the question where it's not symmetrical. No.
Okay, thank you.
Yeah, no problem. So 42 is luckily the last question from 23. So there we go. We made it through 23 almost already. Let's see how long this is though. So a very large conducting plate lying in the XY plane carries a charge per unit area of sigma. A second such plate located above the first plate at that distance above, oriented parallel to the XY plane. Yeah, okay. Carries a charge per unit area of -2 times that. Find the electric field for Z is less than 0, and Z is between 0 and the height of the thing, and Z is then the height is above it. So what's happening is that we have a plate like this. Right underneath it, we have another plate. This top plate has a charge of -2 sigma, which is just charge per unit area. I guess I should draw that in red, shouldn't I? -2 sigma. And then down here we have a charge of sigma, or just 1 sigma if you want to say that. But yeah. So 1 coulomb per, well, it doesn't matter. We don't know what that is, but 1 times the charge per unit area. The other one up top has -2 times the bottom one. So we need to find the electric field for down here. So there's 3 positions. I'll mark them. Down here, in between, and above. So that's A, that's B, and that's C. Okay, well, first what we got to do is find the electric field caused by a plate of charge. I guess we assume that we're near the center of it. We have to make some assumptions here. So I guess we have to assume we're not near an edge, because that gets more complicated. Yeah.
I think this is just supposed to be an infinite plane. Like, that's how you're supposed
Oh
to.
yeah, it says very large. You're right. Very large plate. So they're infinite plates. There you go. So we're definitely not near an edge, because there are no edges. And so to do this, we need to figure out what's the charge that's caused, the electric field, sorry, that's caused by a infinite plate. And there is a formula for that, I'm pretty sure. Yes, so as long the electric field can be described by the magnitude of the electric field caused by an infinite plate can be described by Q over 2A epsilon naught or sigma over 2 epsilon naught. Okay, so there we go. Find the electric field. So as long as we're close to it, find the electric field for Z is less than 0. So I think what we have to assume is that, let's see what the answer is quickly. This is 42. 42, let's see.
Isn't just sigma, like, then it's just assume it's like the plate that's like closest or something? If it's like above or below, and if it's in the middle.
I think it actually wants both. It actually wants, but how is that different?
I'm assuming you add them together.
No, because I think if it's on the bottom, you just do sigma. If it's in the middle, I think you add them together, and if it's above, you just do -2 sigma.
Here, I'm looking at the solution here. So this is what the idea is. Okay, so yeah, this is probably a helpful table. Let me just show the table here.
I like tables.
So if we're below Z equals 0, right, then the electric field from the lower one is in the negative direction, the lower one. So if we're here, then the electric field is in the negative direction, right? Because this is a positive plate, so it points away from it. And the electric field from the top one is in the positive direction. So for part A, right, we have 1, so this is from the -2 thing, and this is from the positive thing. Wrong pen. Sigma. So the net electric field is going to be, so the positive one, which is just going to be sigma over 2 epsilon naught minus 2 sigma or minus 2 sigma, minus 2 sigma. No, well, you take the absolute value there. I don't think we count that negative. Yeah, minus 2 sigma over 2 epsilon naught. Hold on, but that's not the same thing here. Oh yeah, that is the same thing here. Yeah. So then what this ends up being is it's going to be sigma. That's a sigma, not a 6. I know it looks like a 6, but not really too much I can do about that. Minus epsilon over epsilon naught. And that value is, it can simplify into, this is just going to be, I just take it from here, sigma over 2 epsilon naught. So again, from a point underneath the plane, we have one electric field vector going down, and then if I define this as positive, in the negative direction, because it points away from a positive plate. Oh, sorry, this is from the sigma, and this is from, I made the vectors wrong. There you go, other way around. So sorry if that made any confusion. This one going down is from the positive plate. This one going up is from the negative plate, because electric field points away from positive charges and towards negative charges. So that's for part A. For part B, we're going to be in the middle there. Let's take a look at what kind of vectors are going to be acting here. So away from positive charges, that means this is pointing up and towards I'll draw it a little bit bigger. So this is pointing up there from the positive plate and towards negative charges, also up. So they're both pointing in the same direction this time. Both pointing in the same direction. So our total electric field is going to be, first of all, they're both going to be positive, and we just have to add them together. So it's just going to be, it's just going to be, I just take the absolute value since I've decided the directions here. I don't have to do the negative things here. I've decided the directions myself. So it's just going to be 2 sigma over 2 epsilon naught plus sigma over 2 epsilon naught. And this will simplify to 3 over 2. Yeah, 3 over 2.
Just ignoring the negative 2 sigma?
I'm not ignoring the negative. I'm not ignoring the 2. I'm just ignoring the negative. Technically, there's a negative here, and this sigma would be negative 2. But since I'm deciding the direction myself, I can drop the negative.
Okay, all right.
Right. That negative only affects direction, so I'm figuring out the direction visually here, so we don't have to worry.
Cool.
Okay, epsilon naught for that one, and then finally for C, the net electric field is going to be, okay, so up here we have one pointing up from the positive plate, and then another one pointing back down to the negative plate. So it's going to be, one's positive, that's the one from the positive plate, so epsilon over 2 epsilon, sigma over 2 epsilon naught, and then minus 2 epsilon, I keep saying the wrong word, 2 sigma over 2 epsilon naught. So this will be the same as the first one, won't it? Yes, this will be the same as the first one. Or negative of the first one. That doesn't quite make sense because it's the same thing. See this for a second. Yeah, something doesn't make sense here. Hold on. This one was positive, this one's negative. There's the mistake I made. That's because I made a mistake drawing it here, and then I made a mistake with the sign. So note, the green one, the sigma one, is going down, and this one is going up. This value is correct. This value is correct. I just copied it from the answer. That's the problem with copying from the answer. So then this one is going to be negative sigma over 2 epsilon naught. And there we go. Again, I know these look like 6s, so it really should. But yeah, there we go. So those are our answers. Just look at the electric field. This one and this one. Those are our 3 answers. Okay, any questions about here? We made it through chapter 23. Good. I thought that would take a little longer, but I'm happy that we made it through. So now, any questions about all of this? What we just did. Gauss's law is pretty much what we did right there. Just a bunch of Gauss's law.
I got a question about these like regions that we're talking about.
Yeah.
This Z variable. It's kind of new to me. I don't remember seeing these in the lectures. So I just want to know when Z is less than 0, does that mean it's below the sheet?
It's
Or
below
means
the bottom plate.
so in this system there's always 2 sheets.
Yeah, there's
There are
always
2 plates, I guess.
They're infinitely big, so they go forever.
Yeah, so with these Z variables, they only apply to large plates or 2 large plates. A system of 2 large plates. That's when Z plays a role.
Well, not necessarily. I mean, Z is just saying that there's a 3D. We're in the 3D axis, so we have a flat plane. You're coming perpendicular to the flat planes. So I guess they're useful with flat planes. But
So like
they're useful
X,
in
Y,
general.
Z.
X, Y, Z. Yeah, exactly. It's the third
Oh.
dimension. You're just going
Okay.
perpendicular.
Yeah, that
to the 2
makes
planes.
much more sense now. Okay.
Just a quick question.
Yeah.
Why did we disregard all the other directions? Why did we only solve for Z?
Because it said find the electric charge for Z less than 0, Z between 0 and Z naught, and Z greater than Z naught.
So that he only wanted the Z component of the electric field, or the other component.
There is no other components. The other components are 0. The electric field caused by an infinite plate of charge is constant regardless of the distance from the charged plate. So it's and it's always pointing directly away from the charged plate. So it's always pointing straight up away.
Okay, perpendicular to the sheet. Okay.
Yeah, it's always.
Now it makes sense. Okay. Thank you.
No problem. Okay, so yeah, if there's any more questions, go ahead. Otherwise, I will move on to chapter 24, which is electric potential.
I think it's snowing outside.
Snowing? It's definitely.
Yes, I swear.
Definitely cloudy.
Yeah, I saw a bit of snow not too long
Really?
ago.
Yeah, it's snowing.
I'm surprised.
I swear it's snowing.
Adam,
Yeah.
the electric field away from just like a infinite charge plate is just sigma over epsilon naught, right? And they
Yeah.
just like give us the 2 and whatnot. Okay, so it always points away from it, like on either side, right? It would be pointing directly away from it on either side.
Directly away from it or directly towards it. It depends on exactly what's happening. So
The charge, right?
It depends on the charge of the plate. So
Yes.
if the plate is negatively charged, it's directly towards it. And if the plate is positively charged, it's directly away from it.
Right. Okay. Yep. Okay. Thanks.
That's what was changing when I go from the below to the middle to the above. The directions were changing, so that's why.
Right.
Okay, so we're moving on to chapter 24, which again is electric potential. I will definitely need some formulas for this section. I have my formula sheet here though, so let's take a look. And let's see how it goes. So, how much work is done by a battery, generator, or some other source of potential difference in moving Avogadro's number of electrons from an initial point where the electric potential is 9 to a point where the electric potential is -5? Okay, so work done is what we're trying to find. So change in potential energy, I guess. Let's quickly see how much work was done. A minus VP. So I have a formula here that says, it looks promising. Q times VB minus VA equals negative work done, negative work. Looks promising. I think that might be right. I don't know. Let's see. So Q, what's Q in this case? What's Avogadro's number of electrons from an initial point? So an electron has a charge of E, negative E. So we just want to do 6.2023 times 10, no, 6.02 times 10 to the 23. Times 10 to the 23 times negative E. So that's our Q. And VB, someone's got their mic on again. Could you mute? So the VB is electric potential at 9 volts to that. So -5 minus 9 equals negative work. I'll try it. I'm not sure. Let's see if that worked. So it's going to be 6.02 times 10 to the 23 times E. E is 1.6022 times 10 to the negative 19 times, I guess, times negative 1 times negative 5 minus 9. So the amount of work that I got done here, so work, not negative work is equal to negative 135,0334.16 joules. So let's see if that's right. This is, I'm in the wrong section, 23.
I think you're missing a negative.
Yeah, somehow I lost the negative. I don't really know where, though. Where did I lose a negative?
I think that equation is for the potential energy, so it's negative of that.
But
The equation I have here is
because it's negative E times negative 5, negative 9, right?
So that's a positive number, right? So that.
Yeah. So then it's negative work.
So then this would be negative.
Yeah, the work should be negative, yes.
But the answer is positive. The answer is positive in the book.
This doesn't make sense because like the charge of the electron is negative.
It does make sense.
The equation that I
you
have
for
for potential is delta U is equal to Q delta V.
Isn't it
So
negative?
you should end up with a negative delta U, right?
I think this is the absolute value of the charge, not the charge itself. The absolute value, I think. I'm not sure.
Yeah.
Like the charge.
Yeah, I'm not sure.
There's
Yeah.
negative. There's delta V
Yeah,
is equal
it
to
is.
negative E dot delta S. Is that the one that you're supposed to use?
Negative E dot delta S? What's S?
Yeah, I mean we don't know how far we've moved.
We're not
That's
moving.
why I'm
Yeah,
like, I don't know how we can find that.
Yeah. This is the
When
right
you're
number.
checking it further,
I think it's the right answer. It might just also be the error on the textbook sec. It's like
in
it makes
this
sense,
letter,
especially because
they
it's a part.
they equate the potential energy to the work, not the negative of the work.
Oh, I see.
That's what they do.
Yeah.
So I think the potential energy is negative Q delta V, isn't it?
Negative Q
sure.
delta V. Well, no. Delta U is Q delta V. Delta U is Q delta V. Right. Yeah, I don't really know why there's negative work done here. I don't.
We should have positive work though, because we're moving an electron downhill, which is like the opposite of the direction it wants to move.
So
It
it's
wants to
doing
move
work.
to high voltage.
Yeah.
So it should be
You're
positive.
doing work on the system? Yeah. Oh, I reached my limit on Slater, so I won't be much help now. Okay, so yeah, it looks like this should just be... It looks like we just, by reasoning, we know it's going to be positive. I love it when we do by reasoning.
Wait, yeah, then it is delta U equals Q delta V, because that would give you a positive answer at the end.
Yeah.
Wait, so how do you have
Q
positive?
is negative, delta V is negative, you get positive.
Maybe. Yeah.
That makes sense.
Okay, so I have a formula Q delta V just gives you W, not negative W. Is
Yeah,
that
okay.
wrong?
I don't know. I'm
What
looking
is-
at the formula sheet here. I have negative W. I don't even know if
Oh,
I have this
it's
in my
negative.
notes.
Wait, it says field. Maybe that's not it, Adam. I think the one you're looking at, I'm looking at it too, and it says work done by a field, right?
Okay, yeah, that's true. That's true. It says work done by field. I didn't really look at that. Yeah, you're right. So maybe the field is doing negative work?
Possibly.
Or work...
There has to be work done on the electron, so we know that it has
Yeah.
to be positive.
Yeah, it has to be positive. Okay, we have
So
the
now
answer.
what-
That's fine. Yeah. Yeah, question?
How would we know what formula to use if the formula we used was a field one
It's
on the exam?
it's supposed to be... The formula that we really used was delta U equals Q delta V. And that's it. Delta U is the work done.
And where's this formula, or is it not here?
This formula?
Yeah, U equals, yeah.
It's on the... is it on the formula sheet? I'm kind of surprised it's not.
It is. It is.
It is? I just don't see it?
I mean,
don't
it
see
says UB minus UA.
Yeah, okay. It's written out like fully for some reason. I don't know. It's written out like, yeah. Like kind of more like this, but the idea is there. And that's that. Okay.
the answer was positive in the
Positive.
textbook, right? Oh, okay, yeah. Yeah, makes sense.
And on Slater it was positive. So let's see here. Number 2 is find the electric potential difference, delta VE, required to stop an electron, called stopping potential, moving with an initial speed of that. That's just part A, so we should be able to just finish it right like this. Okay, so we're going to find delta, so delta V, we're looking for potential difference. Well, we know Q delta V equals delta U, right? So we need to figure out how much required to stop an electron. We got to figure out how much work is done to stop it.
I think we can use the energy conservation law here.
So delta.
Delta K equals
delta K plus delta E, delta UE will give you 0.
Yeah. What's delta U though? There's no change in potential energy. It's just
QV.
It would be
QV.
It would just be the
QV.
initial.
Oh, I see. Okay.
Yeah.
That makes sense. Delta K plus Q delta V equals 0. And so then VF minus VI plus Q delta V equals 0. VF is 0 because it's stopping. So then we can finally say that delta V is VI over Q. Right? So then that's just going to be 2.85 times 10 to the 7.
No, it has to be the kinetic energy, right? Not the actual velocity
You're
itself.
right. Sorry.
No worries.
This is K F, and this is Ki. So this is Ki, and so this is 1/2 mvi squared over Q. Thank you. So I'll just plug all this in now. So 0.5 times the the mass of an electron is here. So the mass of an electron is 9.1094.
They said proton, right? They said proton. Oh wait, did they?
Electron first and then a proton.
Part B. That's part B. Okay, sorry.
Yeah. So 0.5 times the mass of an electron was 9.1094 times 10 to the negative 31 times something squared, which is VI. VI is 2.85 times 10 to the 7 over Q, which is the charge of an electron, which is just negative E. Do I do negative? I think I use the negative sign. 1.6022 times 10 to the negative 19. So I get delta V is negative 2309. Let's see. It's an even number question, so I don't have the answer, and I don't have any more answers on Slater.
I can't tell it.
Yeah.
It is the right answer.
That's right? Okay. Sounds good. Thank you.
Yeah.
So that's part A. Part B is asking, would a proton traveling at the same speed require a greater or lesser magnitude of electrical potential difference? Well, what's different? This magnitude doesn't, the charge is the same. The only thing that's different is the mass, right? The mass is different. And the mass of a proton is bigger, right? The mass of a proton is bigger. So since this goes up, the numerator goes up, the quantity goes up, it would need higher magnitude. The answer is higher magnitude. Because delta V equals 1/2 mv vi squared over Q. Technically absolute value, whatever. Doesn't matter because we're doing magnitude, but yeah. Okay, that's part B. And part C is find a symbolic expression for the ratio of the proton stopping potential and the electron stopping potential. So delta Vp over delta Ve. Okay, well delta Vp is this just with a P. And delta Ve is just this with an E. MEVI squared over Q. So we take the ratio of these two things, assuming they're starting at the same speed. Yep, I think that's right. All we have to remember is that this has a negative Q charge, What? Oh yeah. V what? Press C here.
You're gonna need a positive voltage difference to stop a proton.
Yeah. So
So the last one was negative.
this should
We
be negative.
get this for electron or for proton?
This is the electron here because the charge is negative.
Yeah. So the delta V for the electron should be negative, but the delta V for the proton should be positive. It'll
But
also
when
be a different value, but it should be positive.
yeah, it's just that when I take the ratio, I don't get the same number that is in the answer here. For some reason, it's negative on the top.
Why?
Oh no, wait, I'm dividing by. It doesn't matter. Never mind. It's I just realized it doesn't matter. So okay, it's fine. VP over delta VE is equal to 1/2. So it's just MP over ME over -1. That's the only difference, right? So then this is why it turns into negative MP over ME. So it's MP here, and that's the ratio. What cancels if I take the ratio? What cancels? Well, VI cancels, that cancels, that cancels, that cancels, that cancels, and that cancels. So I just have M over ME over -1, which is just what I said down there. So there's that. That is question number 2 done. Any questions? Otherwise, I will move on to number 3. So number 3 is potential difference in a uniform field. So oppositely charged parallel plates are separated by that many millimeters. A potential difference of 600 volts exists between the two plates. What is the magnitude of the electric field between the two plates? Okay. So I think this magnitude of the electric field is going to be the same as before. They're oppositely charged parallel plates with the same. Yeah. So if we go back up to the picture here with plates, if you're in between, they're both pointed in the same direction. Right? They're both pointed in the same direction. So it's just 2 times whichever one. But we don't know which one. Potential difference exists of 600 volts exists between the plates. What is the magnitude of the electric field? Something different I'm supposed to do? No, that seems right to me.
For A, I think we divide the potential difference by the distance. Because I think another unit for E is volt per meter, right?
Yeah, you're right. Yeah, that makes sense to me. Okay, so the magnitude... I honestly don't remember him mentioning that once. The volt per meter thing? Did I just miss it? I feel like
The lab.
The lab included it. I see.
The lab included it. I don't know if he mentioned it, but we also did labs like 3 weeks before we got to the content, so...
So, yeah, I did definitely
I
forgot
think
that.
he did include it in the study hall. He did mention that in study hall.
Just strange things to... It seems like an important thing, that electric field is volts per meter. Right, the electric field... So that's an important thing here. The magnitude... Well, no, the electric field is measured in... can be measured in volts per meter. So I guess we'll say that the magnitude of the electric field is going to be 600 volts per 5.33 times 10 to the -9. No, times 10 to the -3. So this is 600 over 5.33 times 10 to the -3. So I get 1,12570 volts per meter. Let's see if that's right for number 3. 1.13 times 10 to the 5. 1, 2, 3, 4, 5. Yeah, that's good. We're good. So that is A. For B, what is the magnitude of the force on an electron between the plates? So Fe equals QE. Right? So we want magnitude, so it doesn't really matter about that. But so we're just going to take the absolute value of all this. So it's going to be E times 1,12570. So that's just going to be answer times E, which is 1.6022 times 10 to the negative 19. So that's just going to be 1.8036 times 10 to the negative 14 times 10 to the negative 14 newtons. Let's see, 1.8 times 10 to the negative 14. Yeah, that's right. So, any questions about that? Otherwise, I'll move on. How much work must be done on the electron to stop it, to move it? Sorry. How much work must be done on the electron to move it to the negative plate if it is initially positioned that much from the positive plate? Okay, so we know the distance it travels then, right? Because we have the two plates. It's this distance away, 2.90 millimeters. 2.90 millimeters from the positive plate. And we're asking how much work is done to move it to the negative plate. We know that this distance is 5.33 millimeters. So then that distance there is 5.33 minus 2.9, which is, so that distance is the delta, I don't know, delta R or delta Y, I guess I'll call it delta Y, is 2.43 millimeters. Now, how much work? Well, how much work must be done on the electron to move it from the negative plate? So delta U equals Q delta V. Well, we know the charge, right? It's electron. And delta V, well, remember delta V is Q, it's going to be Q times what is it? The electric field times
we
the
know
distance?
we know the change in voltage per meter. So we know how far it travels.
Times delta Y.
Not delta Y.
It'd be negative though, because we're going down to the negative plate.
Delta Y as like from that position is 0. If you put that position 0, delta Y from there, not delta Y, delta Y.
Wait, like
no, that's delta Y, 2.43 millimeters, right?
2.43.
Yeah, 2.43. I'm sorry.
Yeah. That's our delta Y.
Considering that position 0, yeah.
Yeah.
But we have to manually input the sign as negative because, like, we're taking the magnitude of E, so we're going down towards the negative plate.
But it's
because you have to get positive work. You're gonna have negative Q. You need a negative.
Do I need positive work? It's an electron going
down a
downhill.
voltage.
Oh
down
yeah,
voltage.
you're right. So then that's negative.
Can I say something?
Yeah.
I think we're gonna just take the magnitude of force and the magnitude of displacement. Time cos theta, which is 0, which is 1. Isn't that the work?
Wait, but why force? Why?
Work is force dot the displacement, which is force times displacement, the magnitude of force times the magnitude of its displacement times the theta between them, which is 0.
Yeah. You're right. That would work too. So I think let's see if we get the answer the same way there. So yeah, work equals the force vector dotted with delta Y. Delta Y is negative, but so we can we can write this as the magnitude of the force times the magnitude of delta Y times a cosine. Cosine? No, sine. No, it's cosine. Cosine of the angle between those two. Well, what's the angle between those two? The force delta Y is down. Delta Y is down, and the force is on an electron is going up, right? So there it's cosine of 180 degrees between those two things, which is -1. So yeah, so we just get the magnitude of the force, which was 1.8 times 10 to the negative 14, times delta Y, which we said was 2.43 times 10 to the negative 3. 2.43 times 10 to the negative 3 times -1. And let's see if we get the same answer as up here, which we probably should, because QE is just F. Yeah, we'll get the same answer. Never mind. What am I talking about? We'll get the same answer. Yeah. It's not a different way. It's just just slightly written differently. Times 2.43 times 10 to the negative 3 times negative 1. So I get negative 4.374 times 10 to the negative 17 joules. 437. Yeah.
That's what I got using the other method. So
It's also positive for some reason.
I think it's just a typo.
it is positive. What do you mean?
No, I got
But-
a negative here.
Your delta y is negative.
But it's just the
But-
magnitude. We just take the magnitude.
Are we
Oh, you just
moving
take
up
the
or
magnitude?
down?
You're moving. It has to be positive because the force is gonna be pushing in the other direction.
Theta is zero. Theta is zero. It's not. It's going. They're going the same way. You're moving it up, not down.
No, but F. Oh, I guess its magnitude doesn't make a difference. Isn't
The-
Fe
no,
pointing up and
It's
it's moving
it's
down?
moving up. It's the electron is moving toward the positive side of the plate. So it's positive. It's like, oh yeah, it should be negative 4 because
No,
if
no,
it's
hold
going
on.
that way.
But no. But it says how much work is done on the electron if to move it to the negative plate if it is initially positioned that it's moving down. Delta y is down.
Oh.
To the negative plate.
So it's positive work. You're putting
So why
work
did I
in
get-
so you can push it away to the negative because they repel, right?
Yeah, I see how it should be positive work, but why did we not get positive as a number here?
I think
You use
your theta.
magnitudes.
I think the theta is 0. It's not 180.
But they're going in opposite directions. The
No,
displacement
the
is
electric field. The electric field will be on the other way if you had a negative. If you have a negative.
No, electric
Isn't
field electric field doesn't change directions. The force changes directions. Electric field doesn't change directions though. Right? So the
Oh, yeah.
the force is going on a negative charge towards the positive, is going up. Delta y is going down. That's 180. It's a difference of 180 there. Right?
That's actually right.
Remember, it's the force.
Adam,
it's the force applied
yeah,
times the distance. But the distance is going in one. The distance is in one direction because it's a vector, and the force is in the opposite direction. So it'd be a negative. It'd be a negative force if we're considering where it's moving.
So the negative comes out here with the 180. That's where the negative comes from, right? Cosine of the angle between them. So we get negative.
no, but what I think is that so you're looking at the force done or force on it due to the field, right? But if we're doing work on it, that means we have to apply force opposite to the field, which is in the direction of the motion, which is why like cosine wouldn't be -1. You know what I mean? Because yeah, like I agree that the force from the field is in the opposite direction from our motion, which is why you put 180 there. But in order to move it in that field, we have to push force in the direction we're moving it in. You know what I mean?
Oh, I see.
Oh, that's
Yeah.
right. It's like the net force times the distance.
Yes, exactly. So then it would be cosine 0, which is, I guess, +1, right? Unless I'm chopped, but yes, I believe it should be 1.
Cosine 0 is 1. Yeah.
But we don't know the net force because we just know that it moved.
Yeah. So is the answer what you have there, Adam? Like the magnitude?
Magnitude's right.
The magnitude is correct. The magnitude
Okay.
is correct for the answer. It's
Nice.
just the direction. Yeah. But it makes sense to have a positive work because you're pushing into the negative.
So maybe
Yeah,
just that
as
this
long
is
as
another time where we say, by reasoning,
Well-
we have.
No, I mean, I was just wondering because is it because you guys are thinking of it as if it was a positive charge because the electron's negative charge, so it's going
No,
towards
but
the
it's
positive.
negative.
No, we looked at it as I believe you
It's
looked at it
electric.
as the correct charge.
Yeah, we know.
Right.
I see how it makes sense. It should be a positive charge. I mean, it should be a positive work we have here. I mean, it's just how we get that with the numbers is what we can't get right.
I
But
would
yeah.
suggest as a failsafe, if you do this using the change in potential energy, you don't have to worry too much about like the fact that this is negative. It'll come out as positive guaranteed.
Yeah,
like you're
because
going
it's a
to
negative
you're going
charge
to
and
mul-
negative delta v.
Your delta v is going to be negative because you're moving to
Yeah.
the negative plate, and your q is going to be negative. So that'll work out for you.
Yeah, that's true. No vectors going on there. Okay, but that's that. That's that question. So let's see. That's question 3 done, I think. Question 3. Let's move on to question 6. Oh, time went fast. It's already been an hour and a bit we've been going for. So question 6 is this the whole question? No, it's a long question. The goal is to get 5 more questions done today. That's the goal. If we can do that, then we can stay on track for tomorrow. So this one isn't going to help us in that goal, though, because it's pretty long.
Well,
boy.
the first few things, they're just a couple of sentences to answer.
Okay.
Whoa, I don't need to scare me like that.
Okay. So let's see. Well, you want better to see the whole thing. So a block having mass m and charge q is connected to an insulating spring having a force constant k. The block lies in a frictionless insulating horizontal track, and the system is immersed in a uniform electric field of magnitude E, directed as shown. The block is released from rest when the spring is unstretched, x equals 0. We wish to show that the ensuing field of a magnitude. Yeah, sorry. For a second I was like, wait, a magnetic field? No, magnitude. We wish to show that the ensuing motion of the block is simple harmonic. Okay. Consider the system of the block, the spring, and the electric field. Is the system isolated or non-isolated? Probably isolated. Let's see. Consider the system of the block, the spring, and the electric field. Is there any other work being done on it? It's horizontal, so gravity is not doing any work. And it's insulating, so heat, I guess it means it's not getting out. Frictionless, friction is not slowing it down. I think yes. Don't see why it wouldn't be yes. Let's see. Yes, the system is isolated. Okay, good. So for part A, isolated. For part B, what kind of potential energy exists within the system? Okay, well, we have, let's see, what kind of potential energy do we have within the system? We have spring potential energy, so spring. Not gravitational. We do have a voltage difference, though, right? We have electric potential. And that should be it. That's all the potentials.
Adam, quick question. So, so they're saying it's released and it's stretched, right? So does it still, do we still have electric potential if it's completely stretched out? Because I guess in a way all of the spring would be converted to electric potential, but I'm not too sure.
Well, no, it's released from unstretched. It's released from x equals 0. So
okay,
it
yeah.
So I guess the spring would have no potential, but I think they just mean in the system, within the whole system. What kind of potential energy we have? Spring, electric. Doesn't really matter at a particular moment. What does it have? But yeah.
Okay, yeah, cool. Well, yeah, I guess it doesn't really specify
a time.
The
right?
plate, yeah, the time, or yeah, exactly, or like where the plate is or something.
Position. Yeah, exactly.
Cool.
So part C is call the initial configuration of the system that exists. Initial configuration of the system that existing just as the block. Am I reading something wrong? Call the initial configuration of the system that existing just as the block is released from rest. That exists? Is that what it's supposed to say? Exists? Just as the block is released from rest. The final configuration is when the block momentarily comes to rest again. What is the value of x when the block comes to rest momentarily? Okay, well, which way is it going to go? It's a positive charge. Right? It's a positive charge. The electric field is this way. So a positive charge will go in the direction of the electric field. So it'll go this way. Okay. And then let's see. What distance? How do I say the distance?
Just do equilibrium. Like
I think the question asking for
the
symbolic.
spring and for the electric force, they have to be the same.
So the force on the spring and
oh wait, no, but this is energy. I don't think they want us to use force.
I think that we should use the potential energies and the kinetic energy as well. So we have spring potential energy.
Yeah.
Like conservation of energy.
Conservation of energy is the easiest. Yeah.
Delta K plus delta U equals 0. So delta K is 0. Right?
At the beginning is 0.
And at the end it's 0. It says find the the final configuration is when the block momentarily comes to rest again.
Yeah.
Yeah, you're right. Yeah, that's right.
So
So,
U.
so yeah, K will be 0.
Yeah. So
because-
UF equals UI. This is what we're saying here, right?
But we have two kinds of potential energies.
Yeah, I understand. Yeah. So UF is going to be, I forget what it was, 1/2 K delta X squared.
Yeah.
That's what it is. And since the initial position was 0, that delta X is going to be our final position, which is what we want. And
So-
initially, yeah.
No. I'm just agreeing.
Yeah.
So-
And so then here we have this, which is just going to solve for delta X.
No. Oh yeah. Shit. I'm looking at this letter. They have the answer in E, and K and Q.
Yeah, I have it here
In
too.
terms of-
Wait, don't we have any electric potential in the beginning?
Yeah. This is Ki. This is electric. Sorry, this is a potential at the beginning. So it's only electric potential, and there's no spring
Okay,
potential.
I meant finally. There's electric potential in the beginning and at the end, right?
Yes, but we could kind of set our endpoint as like a 0 electric potential, because you're allowed to set the 0 for potential energies, aren't you?
You are, but I guess the energy of the system, like the energy of the system fluctuates between these two things, right? All spring potential and all electric potential. So I think this is right still. Let's see. I mean, I think we'll get the right answer. Oh wait, no, but it's a square. Why are we? I'm gonna have a square root to find delta X, and that's not in a square root in the answer. So is it the force is something else? Delta V.
Yeah.
What's delta V? Delta V is the electric. Oh yeah, the delta V is the electric field times delta X. Right? Delta V is the electric field times delta X. So what I can do now is I can just cancel one of those off, and then this is just going to be delta X equals Q E times 2, or 2 QE over K. And there you go. That's the answer. I'll just write it. Well, that's it. That's the answer. So I sub this in to there for delta V. And there we go. Our final position is 2 QE over K.
Adam, the delta V is equal to the field times delta X, because just we kind of derived that just from the units, right? Like volts per meter.
I think so. Yeah, I think so.
Yeah, because I like you said, like I don't recall too much of that either.
Yeah, exactly. I don't know. Yeah, I don't remember mentioning it.
Delta V
Well,
is
okay.
E dot delta S. That's
Yeah.
an equation you can always use.
Oh, okay. Delta V is
Yeah,
E vector.
I have a.
DS.
Oh.
The magnitude actually. Is it?
It's not
I thought it
magnitude.
was-
It's a dot product.
I think E is the derivative of V over the derivative of.
Oh, it's negative. Sorry, negative E. Negative E, not positive E.
Here.
Negative E dot delta S. That's what
Yeah.
it says in the formula sheet.
I can't.
One
For some
quick
reason, I can
question.
never find anything on this formula sheet. I don't see.
I'm using Jasper's. Did you make your own?
No, I just have. I think this is the school one. This is like the.
Yeah, I found the school one to be very like mix and match. Like nothing's really like organized.
Yeah.
This
It's kind of
this
useless, to be
one,
honest. They have like a whole bunch of, they have some, but then others they just don't have.
They
It's
made
kinda
it with
weird
the
when I
intention that we should be able to like derive the rest from the root formula. If that makes
Yeah.
sense.
Yeah.
We
Yeah.
have it in the thing. It's just E equal negative delta V over delta X.
Yeah.
If
yeah.
you
E
look
equals negative delta
closely-
V over delta X. Yeah.
Yeah, so the derivative will be and then just the change of this. So that's what
Yeah.
I guess they did here.
Exactly.
They just put it as a linear and just did the slope.
Yeah. Yeah. No, I know what you mean. Yeah. Yeah. That is what they did. So we are supposed to kind of get the formulas from this. Although I'm thinking there should be a negative here now. So then if there's a negative there now, does that affect this? This would be a negative here. But since Q is no, yeah, wouldn't there be? Oh no, but it's magnitude of the electric field. Yeah, that makes sense. Never mind. Okay, so D is next. So what is the value of x when the block rests momentarily? We already figured that out. At some value of x, we will call x naught. The block has a force, 0 net force on it. Sorry. What analysis model describes the situation? That's all it asks for. What analysis model? I don't know. It's called, according to here, it's called particle in equilibrium analysis model. I guess that's what it's called. Makes sense why it's called that.
It's not simple harmonic motion.
According to Slater, particle in equilibrium analysis model.
Okay. Okay, Slater. Whatever you say.
I don't know.
Isn't
What
it
is the
just-
value of x? Yeah.
Isn't just the conservation of energy? That's all we do.
We did that for here, but now we want to find net zero force on it, right? So to find net zero force, we need, well, we just have to say, well, what are the two forces acting on it? Fe and Fs are the two forces acting on it. Those have to be equal. And so at this value, so Fe is always Q times the electric field, which is equal to Fs, which is K delta X. Negative K delta X? Negative K delta X? No, but we're saying they're equal. So just K delta X. Yeah. Pretty sure. Okay. So we need to solve for delta X. So it's just K E over, sorry, QE over K. That's the answer. Yeah. Equals X naught. That's that. Okay. Then find, so that's E, yeah. Find a new coordinate system, x prime, such that x prime equals x minus x naught. Show that x prime satisfies a differential equation for simple harmonic motion. Find the period of the simple harmonic motion. How does the period depend on the electric force magnitude? Oh boy. Define a new coordinate system. X prime, so that x prime equals x minus x naught. Okay.
Out of the scope of our course, I think.
I'd say so, yes. I mean, checking a differential equation is not very hard. Just show that something satisfies the differential equation is okay. Definitely possible. Find the period of the simple harmonic. But I would say out of the scope of our course. Let's see quickly.
So in the Slater, they just put the...
Yeah.
In Slater, they just put the period equal 2 pi square root of m over k. And then they just solved for the k for the equation that we had. You know? And they just inserted
in one of
that.
these two?
You see the one that you have in the red square? The green square? Sorry.
Which one? Top one or bottom one?
The top one. Yeah,
Top,
this one.
okay.
The delta x equals...
Yeah.
They just solved for x. They just solved for k there, and they just inserted in the equation.
Okay.
So it's mass over q. Whatever. Okay. Yeah, mass over qm over x. Yeah, like x delta x.
Okay. Yeah, that's good. That I don't think we'll need to. Like, we're not gonna get a question that's gonna tell us to define a new coordinate system on the test. So I think we're okay with this one. So yeah, let's move on to the next one. Number 8. If everybody's good with that. Number 8. Do I need a figure for this one? No, I don't need the figure for this one, but just be in the picture a little bit. So here we go. This is not part of the question. It's just part of the last question. So 2-point charges, those two, are separated by that distance. What is the electric potential at a point midway between the charges? I guess in terms of x? No. Is it in terms of x? No, not in terms of x. What is the electric potential? No, sorry. What is the electric potential at a point midway? Oh, I guess exactly midway is what they're asking. Exactly midway between the two. Okay. Well, you can think of it like, let's see. It would be... Okay, let's see if some formula we can figure out.
Just KQ over R, I believe. And then you could just do scalar addition of them.
KQ over R?
That's the electric potential at like any point, right? From a distance
Oh, a
Any
radius,
any
a radius r.
yeah. Oh, so yeah. There has to be point charges though. That formula only works for point charges, which
And
I
this is a point charge. Yeah.
right. Yeah. Okay. Cool.
So
Yeah.
yeah,
So
okay,
then
we're
it'd just
using
be KQ over R.
we're using KEQ over R is the electric potential at a radius r from a point charge. So when we just add those two together, so the potential that we're looking for, the answer is going to be the first one, KEQ. That's actually little q over d over 2. Right. Plus just 2 times that. There you go. Just two times that. Right. Because there's just 2 of them. So
I
let's do
don't.
it.
Excuse me.
Yeah.
So
The
it would be
charges are different. One is +5 and the
Oh,
other
you're
one
right.
is -3.
You're right.
yeah.
Plus KE2Q. Oh, do we know that they're protons? Oh, no, sorry. I thought that we knew they were protons. So this is just capital Q plus KE2Q over D over 2. So we just, I guess I'll factor this out.
Wait,
No,
why
it's
is it
not.
2Q? The charges are complete.
No, you guys are just confusing with the
It's-
picture. It's like 5 and 3 at -3 atom. Like remember
Oh,
the
yeah,
picture's
it's
kind of
5
screwed.
nano.
Yeah.
You're confusing with the picture.
Yeah,
I
it's
am
not
in
the
fact, yeah, exactly. Let's erase that. Okay, so Q1, Q2 is what we're doing. Q1 and Q2. Okay, that's all we need. Yeah, that's it. Okay, good. So now let's do this. So I guess I'll factor out what I can factor out. So KE over D over 2 is going to be times Q1 plus Q2. So now KE is 8.9876 times 10 to the 9 over D over 2. D is 35 times 10 to the, or 0. Let's do 0.35. And then I'm going to multiply that by Q1 plus Q2. 5 times 10 to the -9 minus 3 times 10 to the -9. Nano is -9, yeah. So I get 102.7 volts. 102.7 volts, which is good. Yep, that's good. So that's part A. Part B. What is the potential energy of the pair of charges? What is the significance of the algebraic sign of your answer? Okay, so potential energy between 2 points is going to be that here it's going to be UE is KE Q1 Q2 over R. So KE, actually there's nothing else to plug in. I just plug in the numbers. So it's going to be KE, which is 9 times 10 to the 9, times 5 times 10 to the -9, times -3 times 10 to the -9 over 0.35. So I get -3.85 or 86 times 10 to the -7 joules. Yeah. And then what's the significance of the negative sign? Well, we have a positive charge and a negative charge. So the potential energy stored between them is negative, which means that I have to do work to separate them. Right? I have to do work to separate them. That's what the significance of the negative sign is. And yeah, that's that. There you go. Okay. So any questions?
Just a quick question. Yeah. Sorry. Yeah, just a quick question. Can we use that, like the potential electric potential energy, the total of it is Q1V plus Q2V? Can we use that, or is it kind of wrong?
Can we use, for potential energy here, Q1?
Yeah, Q1V plus Q2V.
Oh, I see. Q1.
Because I used it and I got the wrong answer.
But what's your V though? Delta, it would be delta V. What did you use for
Oh
V?
yeah, I see. We have V only.
We have V
Yeah,
at a
it's not
point
a
between them, right? That's what we have. We don't have other V's to use there, right? The V would be
Yeah.
the voltage difference of them as it moves, which I guess, I don't know. I'm not sure. Yeah.
Yeah.
Okay, so let's see
Makes
now.
sense.
What'd you say?
I said it makes sense.
Okay,
Yeah.
okay.
It's just one. Yeah, it's not different. It's just 1 point.
So 22 is this figure represents the graph of the electric potential in a region of space versus position, where the electric field is parallel to the x-axis. Draw a graph of the component of the electric field, of the x component of the electric field versus x in the region. Okay, so what's happening? We have an electric field that's parallel to the x-axis. This is motion in the x-axis. So as you increase your x, you're going further into the electric field. You increase by 20. And then draw a graph of the x component of the electric field versus x. Well, would the x component of the electric field be constant?
Is this the same thing as like delta V is equal to negative E dot delta S again?
I think what this is actually. What?
The only thing I know about this is that electric field is a derivative of potential.
Yeah, I'm just using a formula here. E equals negative dV by dx. So what you just said. So slope here is 20. So it's 20 and then 0 and then negative 20. That's my guess of what that looks like. 22. No, it's a picture, so I won't be able to see it. Yeah, I don't have the Slater answers anymore. So, I don't know. That's my guess of what this is. What's negative, so would it be like that instead? I'll do it with a different color. Would it be like that instead? I'm not really sure. Does anybody have a Slater answer? Because I can't access the Slater answer anymore.
Yep, it is.
Which one, the green one or the red one?
The green one, the red one, the one with negative.
So like this.
Yeah, the opposite.
Okay, so I'm just using the fact that E equals negative dV by dx. Again, I don't remember him ever saying this one. Maybe he did, actually, and I'm just forgetting it. No, actually, I don't remember him saying this one. So I'm not sure, but a little strange.
Mine did not. Our professor did not. Tian did not. She never mentioned that.
No,
Yeah,
Springer
really.
did. Springer went through a graph question.
Oh, really? And I just don't remember it? Yeah.
And what do you mean by negative? I don't know what you do with the pink and the green. What did you do with those?
Oh, well, if it was just dV by dx, then it would be this green one. It would be this green one. Right? But it's negative dV by dx. So that just means I'm flipping across the x-axis. So it just looks like this.
Oh, okay, I see what you're doing. Okay. Thank you.
No problem. Okay, that's 22. Let's take a look at 24. So 24 is an electric field in the region of space is parallel to the x-axis. The electric potential varies with position as shown in the figure. Graph the x component of the electric field versus position in the region. Same thing as before. So let's just do it. So it's negative. So the slope here is 30. So it's going to be negative 30. Slope here is negative 30. So it's going to be 30. Slope here is 0. So it's going to be 0. Slope here is negative 30. So it's going to be 30. And it's going to look like that. Pretty sure that's right. This was parallel too. Yeah. I'm going to just say that's right. Could someone check the Slater solution on that and just see if it's the same? But yeah, I'm pretty sure that's right.
Yeah, it is.
That's it? Okay, it is.
That's what I know.
Okay, thank you. Okay, so then the last one I have here from chapter 24, so we're making very good progress, is this one. So is number 33. Number 33. A very large, thin, flat plane of aluminum, so infinite plane of aluminum, has that area and that charge uniformly distributed over its surfaces. Assuming the same charge is spread uniformly over the upper surface of an otherwise identical glass plane, compare the electric fields just below the center of the upper surface of each plate. Okay, so let me see for a second here. Yeah, this is going to be... Okay, we have a plate here that has some charge density, right? So the charge density is going to be Q over A. And so assuming the same charge is spread uniformly over an upper surface of an otherwise identical glass plate. So that's the glass plate. And it's just on the upper surface. Just on the upper surface here. There's also another thing. There's also the charge density. Here's on both sides. Compare the electric fields just above the center of the upper surface of each plate. Okay. So we know for this one, the electric field right there, right above it, is going to be sigma over 2 epsilon naught. So that's our formula from before. So that's the electric field right above it. Here, it's a little bit different. And I can't quite remember how we're going to deal with that. So it's just positive there. So is it... Well, it wouldn't be half. No, would it be the same? No, it wouldn't be the same. Because the net charge is half. Yeah. So since the net charge is half in the box... Because I'm trying to imagine, you know, Springer did an example with like a box on a plane. Maybe let's find Springer's lecture.
Is this meant to be because if we have a charge on the upper part of a plate, like let's assume there's some thickness to it, like just as an example, if the top is, let's say, positively charged, then in order to balance out, the bottom would be negatively charged.
Yeah, that's what I'm thinking.
They italicize upper, which is like usually means like this is a hint to the question.
Yeah. I would have said they're different, but I'm seeing the Slater solution here and it's saying they're the same, which I guess would make sense because you have either way, from the perspective of something up here, you have a plate of positive charges pointing up. That's what you have. From the perspective of something underneath, it's different. But from the perspective of something up here, this would have the same charge. Oops, that would have the same also sigma over 2 epsilon naught. But let me look at Springer's lecture on this and see if I can get any kind of information about it. So give me just 1 second here. Let me see if I can get any insight.
Does he like assume it's infinitely thin or something? So like it would just be half the charge.
I would also think it's half, but the answer is the same. But I would also think it's half the charge.
Oh, the answer is the same. Weird.
The answer is that they're the same. Let's see here. So
Wait, but is it logic that someone said if the top is positive, then the bottom has to be negative? That should check out, right?
yeah. So how does that explain that they're the same though?
The
Because-
formula for E for a sheet, I mean a plane, is Q2 epsilon A. Like plugging in for the charge. What was that thing? Yeah, so if you plug in Q over A, then it's just Q divided by 2 epsilon A, right?
Yeah.
Yeah,
Q over 2 epsilon A. Yeah.
Yeah. So for the top layer, it would be that, and then for the bottom layer, it would just be negative. They're both technically magnitudinally equal.
Yeah, they are. Let me look at the Gauss's law thing here. Let me see if I have it here. So this is no, this is just cylindrical. No, nothing really mentioning the one. I swear I remember him talking about one that's like a one-sided plate, but I can't quite remember the difference. So they're equal because my explanation is because from the perspective of something up here, they just see a charged plate. Perspective of something underneath, it's different, charged, not charged. But it would be charged. I mean, it has to have a difference of charge. Or I guess it doesn't. That's a potential difference, but it doesn't have to have a. It could just be the top is positively or whatever charge, but then I guess it would induce the other charge. I'm not really sure. This later explanation is not much more clear. It's something to do with Gauss's law, that's for sure. And yeah, that's about my explanation of that. Does anybody have anything to add for this one?
Oh, I think I have an explanation. You know
sure.
how the aluminum on top is positively charged? Let's just pretend it's positively
Okay.
charged. Then the glass below it would be positively charged too, because the positives in the glass and the positives on the aluminum repel each other.
Are they on top of each other? Are these two plates like assuming the same charge spread uniformly? I don't think they're like next to. I don't think they're supposed to be interacting with each other in any way, though.
No, but like if you oh wait, oh, but here on the later it basically says that both fields are equal because the aluminum and glass plates are directly vertically upwards. The electric fields above aluminum and glass plates are directly vertical.
Yeah, that's just saying what I'm saying, which is like from the perspective of something above both of the plates, it would be the same. It would be the same. Like it wouldn't change. Nothing would change there, right? So I don't think they're interacting. I don't think they're interacting in any way. We're just supposed to compare the electric fields. So yeah.
Yeah, I think you're right. I think that's the only explanation.
Yeah. Okay. So let's keep moving though. So we're done chapter 24. And we're done so we've finished so far chapter 22, chapter 23, and chapter 24. So we're now on chapter 26. We have 26, 28, 29 to do. So let's get going. Chapter 26 now. We'll start with with question 1, of course. So this is about electric current. Let's see what's it called? Current and resistance is what it's called. So yeah, let's see here. We will take a break at 8 o'clock. So in 10 minutes, we're going to take a break. 20-minute break at 8 o'clock. So let's see here. Definitely recording, but just thought I'd check again. That would be a bad time to notice that I'm not recording. So question 1 here is a 200-kilometer long high-voltage transmission line. That many centimeters in diameter carries a current of 1,000 amps. If the conductor is copper with a free charge density of that per cubic meter, how many years does it take one electron to travel the full length of the cable? Okay, just not too much in this, but just trying to use some formulas. So let me find the formulas. There we go. So we're looking for, so current equals NQAVD. And VD is distance over time. So distance over time. Well, I guess I'll leave it as VD for now. So what is it saying? The current is the free charge density. So that's this N here. The electron is the charge. We're going to use this and, well, area of the cross section. So we just need that to find that. And then here for VD, well, we just have to remember that VD is distance over time. So we're looking for time. We know distance. So that is the distance. And then what we're looking for is how many years is time. And of course, current is current. So let me just sub that in. So I equals NQA. Well, what's A? A is pi r squared. Right? Pi r squared. So it's 2 centimeters in diameter. So that means that r equals 1 centimeter. VD is distance over time. Again, solving for time. So this is going to be time equals NQ pi r squared d over I. And I think I just plug everything in. this will be in seconds, I'm pretty sure. Yeah, seconds. So I'll just have to convert it after. So free charge density is 8.5 times 10 to the 28 times the charge of an electron, which is negative. There you go. Negative 1.6022 times 10 to the negative 19 times pi times 1 squared, which of course is fine, and then times the distance, which is 200 kilometers. So that's 200 times 10 to the 3. Okay. Divided by 1,000 amps. So I get my answer is, oh, it's negative, because I put a negative for the Q here, so I guess we don't need negative Q. I guess we only talk about flow. So I guess it doesn't matter. I'll just make it absolute value. So 8.55688 times 10 to the 12 seconds. So that's seconds. So let's see, what conversion factor do I need for 8.55688 times 10 to the 12? So that's seconds.
I believe that's teraseconds.
Teraseconds? Yeah, I guess, yeah. But how would I convert that to... Yeah, I mean, anyways, I'll just do it like this. So, minute per second in 1 minute is 60 seconds. Hour per minute in 1 hour is 60 minutes. Day per, day per hour. In 1 day, there's 24 hours. And then years per day. In 1 year, there's 365 days. So I will take this number divided by 60 times 60 times 24 times 365. So I get 271,336 years. That seems a little bit like a big number.
I think you did a typo because you have all the right numbers.
Yeah.
Yep. The answer is 27.
Yeah, the answer is 27. I see that. Yeah.
I think it's because you used 1 instead of 0.01.
Oh, yeah, you're right. I did 1 meter instead of 1 centimeter in my answer here. So, yeah, let's do that. That would be times...
So it's to the 10 instead of to the 12.
Yeah. 1 times 10 to the... Or no, I got times 10 to the 11 here. I got
Isn't centi like meters times 10 to the negative 2?
Yeah. Yeah, it is. But then it's squared. Oh, that wouldn't make anything better. But I'm typing into my calculator.
Yes, it was.
What'd you say?
Yeah, the time is actually 8.545 to the exponent of 8, not the exponent of 11. So yeah, it will make.
Oh, wait. So 12 minus 4, because we do 10 to the negative 2 squared would be 10 to the negative 4.
But why is my calculator giving me just a different exponent? Times pi times 0.01 squared times distance, which is 200 times 10 to the 3. Oh yeah, sorry. Then divide by 1,000. I wasn't dividing by 1,000. Yes, so it's 8. Yes, I get 8. 8 there. Okay, there we go. So now do that times 10 to the 8. So then this one. I go here. Yeah. So yes, I get 27 now. 27.13 years. Yeah. That was the problem. I just used meters instead of centimeters. Okay. That's question 1 done. Any questions about that question? And let's see. Question 1 done now. Number 2. Probably won't have time to finish number 2, so we will take a break right at 8. So let's at least give it a read. So a small sphere that carries a charge q is whirled in a circle at the end of an insulating string. The angular frequency of revolution is omega. What average current does this revolving charge represent? Okay, so current is dq dt, right? Current is dq dt. And so, well, what's the rate of change of charge? What average current does this revolving charge represent? At a particular location. Yeah.
I think that the time they just equal it to the period.
Yeah. Oh, so well.
Yeah, the change of time is period. Like T1 minus T2, I think is the period. I don't know. They just equal to the period, to be honest.
They make it equal to the period, but then that would be the rate of change. But that's not what. Because like current is the rate of change of charge at a point, at some point. Or is it at some point? Or just through something? What average current does this revolving charge represent? Well, that would just be delta T omega. Going back to my other stuff, my wave stuff. Omega is 2 pi over t. Yeah, omega is 2 pi over t. So
yeah,
so
we don't have anything related to that in the sheet that they provide to us. There's nothing about revolving stuff.
I'm really
I guess
not sure.
T is the only time constant we can get out of the information we're given, though.
That's what I think, right? That's what I'm thinking.
Isn't velocity just r omega?
Velocity r. What's r? Oh, the radius of the thing.
Yeah, isn't it that?
That's not known. We don't know the radius.
Oh, yeah.
Yeah, that's true. Okay, guys. Well, it's 8 o'clock, so let's take a 20-minute break, and then we'll finish this after. But yeah, so good. We made all the progress that I was planning on making today, so I'm happy we got here. And so we got a lot of questions left. I mean, 26, 28, and 29, but 28 is the only thing that has a bunch of problems. But that's good because we need to practice magnetic fields. We haven't done that yet, so yeah, there's that. Okay, so let's finish. Let's have a 20-minute break, and then we will come back and to complete this and see how many more questions we can do in the 40 minutes after. So yes, there is our break screen, and I'll just leave it at 21. There we go. It's already set up for me. Okay, so back in 20 minutes, guys. Okay, hi everybody. I am back. Can someone say something quickly? See if I can hear them.
Hello, welcome back.
Okay, yes, I can hear. So, how's everybody doing? Hopefully, we've got a good break. We will continue now to. There we go. There's the screen back. Okay, good. So yeah, let's continue. We just stopped at question 2. We didn't finish question 2 because we didn't understand question 2. So I didn't think about this in the last 20 minutes. So did anybody get any progress on this in the last 20 minutes?
So apparently current is just the total charge divided by the total time.
Not the time, the period. Like, I don't find any explanation.
The definition of current is charge divided by time.
Okay, so we just take Q divided by 2 pi omega, 2 pi over omega.
Yeah.
Yeah.
So it's just gonna be omega Q over 2 pi.
Zero explanation though. No one explained anything, to be honest.
I mean, in
but
general,
it makes sense.
Charge over time. Yeah, current is charge over time. So we take the charge over the time.
How is the change in the charge is the same as the charge itself?
There's only
That does
one
not
charge
make sense
moving.
to me.
Okay,
Well,
the fundamental definition of current is the total charge divided by total time. Like charge per time. That's the definition.
Isn't it current the change in the charge over the change of the time? I understand the change of the time being the period. I can understand that. I can see that happening. But I don't understand how the change in the charge is the same as the charge. Unless the charge is just constant.
I think what it is it's the charge like through the system, I guess. Like
it's constant?
Well, it's constant.
So they just assume this constant and it's never changed, so they just put the same charge?
Well, but dq then delta q would then be 0, right? It wouldn't be q.
Oh yeah.
So that's not quite it. I think just in general, current is charge divided by time. Charge per time.
Oh, yeah, guys. Remember, the change of charge over change over time. That's the instantaneous current. They're asking for average current. Average current is a total charge divided by total
I
time.
see. I guess so. Yeah. Okay. Average current is total
It's
charge
in the
over total time.
textbook. It's literally the first equation in 26.1.
Oh, I see. Okay.
That makes sense. Yeah. If it's the average, yeah.
Yeah.
Okay.
It makes sense to me if it's the average. Yeah.
There we have our answer. So let's take a look
Yeah.
at the next question, which is number 5.
All about calculus.
What'd you say?
It's all about calculus, this one. Like it's all about integration and
this one here?
Oh,
really?
Yeah.
Okay. Suppose the current in a conductor decreases exponentially according to time with this equation, where I naught is the initial current at time t equals 0, and tau is the constant having dimension of time. Okay. Yeah. Consider a fixed observation point within the conductor. How much charge passes in between this point t0 and t equals tau? How much charge passes this point between t equals 0 and t equals tau?
Hey, wait a second. This looks familiar.
It does look familiar.
Really?
Yeah. So
I think
we have
guys, we're using an inductor for this question.
Let me see. Well, I can use an ELE formula, but what do we know from here?
Can I say something?
Sure. Yeah.
Yeah. So yeah. So they just want the change in the they want the delta charge. So dq basically.
dq.
So I is dq over dt.
Oh, okay.
Yeah, that's what I said. It's all about integration.
Oh, I is dq by dt. So then.
Yeah.
So I of t.
Yeah.
So then we say I of t dt. So we say that q is equal to the integral from 0 to tau.
Yeah. With respect to t.
Okay.
But they said they will never ask us about integration, so that's.
Yeah, I see. So should we just skip this question if we're not going to be asked about integration?
Yeah, I think we can.
Is that good with everybody? This is an entirely integration question. It's probably all like this.
Yeah, you just change the limit, like
You
the
just change
upper,
the
upper
limit.
limit.
Yeah.
Yeah.
So there we go. That's it. You do this integral for 3 different limits. Right? Those 3 limits, and there you go. Okay. Let's call that done for question 5. Question 10. We have this is the resistance section now. So question 10 is a wire 50 meters long and 20 millimeters in diameter is connected to a source with a potential difference of 9.11 volts, and the current is found to be 36 amps. Assume a temperature of that using some table. Identify the metal out of which the wire is made. Okay, we need to find this table 26.2.
I will just send it. Just wait a second.
You'll send it? Okay, thank you.
Yeah, I'll send it to the Discord.
Can you put it in discussions?
Yeah, I will just paste it there. Go to Discord. And there you go. I sent
we're
it.
going to be solving for an n value, right? Because that would be the thing that changes.
I gotta look at this. I gotta look at this thing here first. I don't know where we're looking quite yet. So
I forget that.
mhm.
Is it okay? Is it highlighted, or do you want to send it again without the highlight?
That's okay. That's fine. It's whatever. It's okay. Don't worry. So what do we know? The resistance per. Okay, so length of the wire is 50 meters long, 2 millimeters in diameter. So it looks like diameter is what's important here. Is connected to a source with a potential difference of 9.11 volts, and the current is found to be that. Assume a temperature of that. Find the metal out of which. Okay, so we know that. I think we're supposed to use Ohm's law here. So V equals I R. So 9.11 equals. Oh yeah. I see. 9.11 equals 36 R. Right. So okay. Well, I guess a better way to do it is just keep this in terms of R. R is V over I. R is also equal to no, well, not something that's actually kind of useful. Hold on. You find an R that's useful here.
My bad. That was only for copper. This is for the metal list. My
This
bad.
is for everything?
Sorry. Yeah, this is for the metals.
Okay.
In general, that was only for copper.
Yeah.
Do you
this
have
makes a
the
little.
equation that relates resistance to the coefficient, the temperature coefficient, or whatever?
What's the temperature
Or
coefficient thing?
it's resistivity, I guess. There's a I guess I can send this in the chat as well.
Yeah, it's something like here. Let me see if we're talking about the same thing here.
Resistivity and resistance is what it's labeled in my
Here.
like list of stuff.
R equals rho
Yeah.
L over A.
Rho L over A is the one I'm looking at, and
Okay,
I think
so-
rho is resistivity.
So what does temperature have to do with any of this?
I think that what's the units of temperature? Degrees C.
I think at a specific temperature, the metals will conduct in a different way. Like they will conduct differently. So
Yeah.
20 is basically the room temperature.
Isn't there an other equation relating temperature and resistivity? Like PFT is PFTO. Like this is the one.
Oh yeah,
like,
there is.
Springer gave it to us in his
It's
lecture.
P over here. It's P
I think
in
Young never.
brackets TO. Then another set of brackets 1 plus this. Ooh, I don't know what sign this is.
In another. Hold on.
One.
What am I reading?
It's an alpha.
1 plus
Yeah,
alpha.
1 plus. Yes,
Young
alpha.
never
Yeah.
mentioned the temperature.
T minus
I
TO.
don't know.
And also T minus TO multiplying the alpha.
Oh, T like here is T minus T naught?
Yeah.
Like that?
Yeah.
Is this a function? Or this is like the density or something? Or
I
this
think
is-
it
No,
would be
that's the
a function,
resistance.
but I'm not.
I think that's the resistance.
What is this
That's
equal
the
to?
resistivity.
And what is this equal to?
P is resistivity.
Okay.
I think alpha is the time or the temperature change constant, like with respect, I guess, to time. Oh no,
Is this-
T is
yeah.
temperature. So it's the I think it's probably how much the resistivity changes for every degree you go up, right? Because it's 1 over.
So this is
degrees
delta
C.
R?
I just sent the equation that is in the book
No,
about.
it's P of T. It's rho of T. So resistivity in terms of time.
Oh, rho of t. Okay, rho of t.
In
that?
terms of
Yeah.
time.
I sent the equation to the Discord chat so you can look at it.
Okay, yeah,
I
that's
wrote
a lot
it
easier.
down.
Thank you. Okay, so rho of t equals rho of t naught. So temperature, not time.
Yeah.
Right,
T
temperature.
naught is the reference temperature.
Yeah.
Like some reference temperature.
1 minus. So I never seen this equation before, so I don't really know what it is.
I
But
just
t
sent
mi-
the.
So in
Yeah,
the
let me see.
table they gave us alpha, right? They gave us
Yeah.
temperature coefficient.
Yeah, and t naught.
Yeah.
When did we learn this equation?
It was in
Mm,
Springer's lectures. He's like,
Really?
you guys might need this. He's definitely not on the exam, but you guys might need this on the homework. That's what he said.
Oh, okay.
Young
Interesting.
never explained this one. Young never explained this one. Anyone from Young's?
Mm-hmm. So at a certain, so how do we even use this though? Because we know assume a temperature of that, and then, so this is this gonna, this equation is gonna fit in here for this at this temperature. So R equals this whole thing, P of T naught, 1 minus alpha of T minus T naught. But what's T and what's T naught? And then also have to multiply by L over A. Is that what I'm supposed to do? Is that what you're saying? Whoever's, I don't know who you is in this. Just whoever's suggesting.
Well, I
things.
was guessing you have to use alpha in some way, and that's the only equation with alpha in it.
Yeah, yeah. That makes sense.
Because to identify the metal, you either have to find alpha or the resistivity. That's like the only way you can find.
Would
Yeah,
T
what am
naught
I
be
solving for? I just
absolute
realized.
Zero.
What'd you
Or
say?
would it
Sorry?
be
What
something?
was it?
Would T not be absolute zero? Or would that just be a bad assumption? Like
No,
I'm trying to think
that's
of
a
how they would.
reference temperature. Some reference temperature where we know the resistivity.
Do we have that though? We don't. Oh no, we have any of these. Any of? Oh no, but we don't know the material. Sorry, we don't know the material.
And that doesn't list what that. It gives you the resistivity on that chart, but it doesn't say at what temperature. It just says this is what it is at some point.
Well, I guess it gives you 1 over the temperature.
So, excuse me. I just opened Slater for this question, to be honest.
Yeah.
I just checked it. They are using the equation that they just sent, like the density sign, but it's not used for density here. I don't know why. Equal resistance times the current over the length of the thing. And then they just found the the.
Can you
What
send
they
it to
call
the
it again?
chat, please?
Yeah. Can you
Yeah,
send it like a
I
picture?
send it. I send it. It's already there. I think
Oh.
I sent it. It's the one, like, yeah, the one that is on top. R equal P, and they just solved for P for the.
Wait, what? Where?
Yeah, this one, the one that you just tagged. I will just send it again, just a minute.
Yeah, this sigma over A. This one.
No,
But
can you
what?
send this
Yeah,
later
this
thing?
one.
Oh no, this isn't resistance. This is that.
I'll just send it again. Here you go. They use this equation right here. You know, I'll just send the page
Yeah.
for the
Yeah.
from Florida. I'll just show you what they did.
Oh, we have to find R. I think this is easy. So you have to use R equals rho L over A, and you have to find R using Ohm's law, and then you just have to plug it in, I guess.
And then this is V over I, or hold on, V equals V equals IR. So I'm solving for R. So yeah, V over I is right. And I'm solving for what though? I'm solving for rho.
Yeah, yeah.
Oh yeah, yeah. That's
I don't know.
that worked. Yeah. There we go. I don't know. Yeah. Okay, that's fine. V over I. So VA over IL. There we go. And we just plug everything in now. Yeah, that I don't know. Okay, yeah, that's fine. That
I
was a
think
lot.
they give us the temperature just to make sure that it's a room temperature. Instead of saying room temperature, they just said 20.
Okay, they gave it to us like that. Yeah, okay, I guess so. So
Think
V
so.
is 9.11. A is pi r squared. So pi. It's millimeters, so 1 times 10 to the negative 3 squared. The diameter is 2. So the radius is 1. And then that's A, and then IL, so I is 36 and L is 50. Okay, so this will be?
According to the table, silver.
Yeah, let's see. 5 times squared. 1 times 10 to the negative 3.
Yep.
Bruh, that was easy. Sorry for throwing us off.
Don't worry. Yeah, 1.58999 times 10 to the negative 8 something, whatever it is. But it's 1.58? So 1.59 is this one right there. So it looks like silver is the answer. Yes. Therefore silver.
You know, this is the first time I ever hear about this problem.
Yeah, of something like this?
Yeah. And it's like just dumb. Just say room temperature. You don't have to say.
I know, yeah. That definitely was on purpose to throw us off. Right? Okay, so 13 is our next question. So here we go. Suppose you wish to fabricate a uniform wire of 1 gram of copper. If the wire is to have a resistance of that, all the copper is to be used. What must be the length of the wire and the diameter of the wire? Okay, that's not too bad. So R equals rho, what was it, L over A? Or A over L? L over A. Oh, is it L over A? Yeah, L over A. So what we're looking for, what must the length and the diameter of the wire be? We can find the length. We know the mass of it. We know the resistance, so R is 0.5. We looking for the length. We're also looking for the diameter, though. So we can replace A with pi R squared. Or I can say pi diameter over 2 squared. So we have, rho, we know it's copper, so we know rho, it's fine. We have 2 unknowns, 1 equation. Yeah, that's a problem. Let's see. Okay, first of all, let's find rho. Rho for copper is 1.7 times 10 to the negative 8, I think that is. 1.7 times 10 to the negative 8. Rho is 1 negative 8. So I can rearrange, but that doesn't really help me because I don't know one of the 2 things. So I have to make another equation probably. So, no, but because then I can say, okay, do we use this equation now for copper? But we don't have any temperature information. I haven't used the mass, so that's an important thing.
We can assume just room temperature. Can't we assume room temperature?
It doesn't even mention it, so it doesn't seem like we're supposed to use temperature in any way. We haven't used the mass though, so that's definitely what it is.
Oh, wait. What's the linear mass density of copper?
Linear mass density of copper? Yeah, that's
that
probably.
Would give you length, because you know.
Isn't that also rho? Or am I thinking of something else? Maybe rho
I don't remember.
No, linear mass density was lambda.
Oh.
Was it? I don't.
No, that was linear charge density. Sorry, it was linear charge density.
No, that's mu, right?
Mu is linear mass density. Yeah.
Because if we know mu, and that's probably in a different table, you can find.
That's true.
The length, because you know.
Which is mass, so mass per length, which is the same L there. And yeah, then we would have 2 equations, 2 unknowns. Yes, that works. So let's find the linear mass density of this. I guess I'll look in the textbook.
Wait. Yeah, okay, let's do that. I'm trying to think, wait, if you have a really thick wire, your linear mass density would change, right?
See, this is now confusing.
That's the only way I can think of getting a distance from a mass, is you have to have a way of relating
Yeah,
like
I agree.
mass per length.
I guess I'm just gonna Google it. I can't find it in the textbook, so I'll just say linear mass density.
I would just linear mass density. I can give you the density.
Of copper? Do you have it? Well, I have it here too, but is it the same number?
Yeah.
Like,
Yeah, it's 8.92 times 10 to the 3.
yeah, 8.92 times 10 to the 3. Yeah.
That's the density.
Is equal
And
to
resistivity from the same table, we have it 1.7 exponent -8 from the same table that I just sent right now.
Oh, so it's
The
okay. So
table-
it's right. Like you're saying, it's like it's gonna be right. Yeah. So now I can say that. Yeah, I can say L equals M over 8.92 times 10 to the 3. And I can rearrange. I can sub that into here. So that'd be R equals subbing in L. So I'm gonna solve for D. It's gonna be a little messy, but 8 point. You know what? I'll just call that mu still. I'll call that mu still. Say mu equals over pi diameter over 2 squared. So R equals. This is gonna be rho. Let's see what's gonna happen. It's gonna be 4m over pi.
Isn't A supposed to be like the cross-sectional area or something? How did you get L into A?
That's a D. That's a D there.
Oh, okay.
That's diameter.
I was
Diameter.
like, why did...
Yeah.
Okay.
Diameter over 2. Yeah. Fair enough. Fair enough. So let's solve for diameter now. So that's going to be diameter equals rho, 4 rho m over pi r mu. So 4 times rho, which is 1.7 times 10 to the negative 8 times 0.01, 1 gram, yeah, over pi times 0.5.
Guys.
Yeah.
I just checked Slater, and they just used the density of copper, which is equal mass over volume, and they use the volume as the cross section, the area times length, and that's how they connect it.
That makes sense. We probably get a different answer than now for this one. I got 4.853 times 10 to the negative 4. Oh, you know what?
He's square rooted. You have D squared.
Oh yeah.
I just sent the equation that they used. I just sent it to the discussion. Did I send it to the right discussion though? Yeah, I did.
Let's see.
One of the pieces density, and the other one is the resistivity. Resistivity. I don't know. Do you want me to send you the screenshot of the whole answer?
Yeah, could you have the whole answer? Yeah.
Yeah. Yeah, just 1 second. Need to zoom in.
Yeah, because this is, I realized, yeah, this is in units of, yeah, hold on.
Yeah, they just use volume and they connect the area, like the volume is area times length. And they
So,
just
yeah.
use that.
So this is actual density. So this is, what kind of density is this? Hold on. This is resistivity? Resistivity.
Resistivity and,
So
yeah.
I'll say R here.
And
rho
resistance.
R. Yeah, rho R, and then rho is the actual rho of the thing, which is mass over volume. So yeah, and then if I want to find volume is the cross-sectional area times the length, which is A times L, which is pi r squared times L. I'll just leave r squared because I don't want to deal with the fractions. So I can rewrite this as rho is m over pi r squared L. In other words, L is m over pi r squared rho. So there is our actual first equation. I mean, our second equation, second unknown, and that's what we sub in.
Yeah, now it makes sense to me actually.
Yeah. So we messed up the units there because this should be mass per volume. Yeah. Okay, so yeah, here I'm gonna sub that in. So it's gonna be R equals rho. Oh, I should be clear what rho. Rho R, the resistivity, times m over pi r squared rho over pi oh, that's the cross-sectional area, pi r squared. I'll just call it, I'll leave it as r instead of d. I'll just leave it as r. And so we're solving for r here, right? Yeah. Okay, so r equals rho r. It's going to be m over pi squared r to the 4 rho. Something's not seeming right here, but let's see if we get the right answer. Getting r now, so actual r. R is going to be the 4th root, so I'm getting a 4th root here.
Oh, damn.
Of rho r m over pi squared r rho.
And what did you find?
Let's see the value. Yeah, let's see what value we get. Maybe I did it slightly differently. I guess because I'm doing r instead of diameter. I don't know, but they solve for radius, so I don't know. It's not gonna be right because they have a different equation. So, but I'll try.
The equations that rely on you to use information that's somewhere else and is not mentioned is really annoying. I have to say.
Yeah.
This is like so much. This is just we're a scavenger hunt basically.
Yeah. 1.7 times 10 to the negative 8 times the mass, which is 0.01 over pi squared times 0.5 sorry, times actual rho, which was 8.92 times 10 to the 3. So I get 2.5 times 10 to the negative 4, which is not the number.
No, it's 1.4. The radius or the diameter?
Radius.
Yeah. It is half of that, to be honest.
Yeah, so what did I do? Did I mess up algebra? Or what do you think I did here? This was rho. I'll leave that.
I think everything makes sense here. Just a minute. I think you substitute for the wrong P.
How? What do you mean?
Oh, okay. Over here, they solved for L, to be honest. So they just find L to be the square root of mass times R, the radius. Not the radius, sorry. R, the rod, over density times the resistivity as well.
Let's see. Are our two starting equations the same? I have resistance equals rho, so rho r resistivity, L over pi r squared, and that's my first equation. My second equation is L equals m over pi r squared rho. This is what I'm trying to solve, right? For r and L, r and L. Do I know everything else? I know this. 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 I know everything else here. Right? So
yeah, it makes sense. It makes sense. What you have there.
So then if I try this again, let's see. Try this again. What were you gonna say?
Yeah, I would say they kept it as an area. I'm trying to understand the question that I can.
I see nothing wrong in your previous equation. It looks like
I need to.
Right. So I think this are they using different constants or does it list the same constants?
Okay. So that's what they did. They did mass over density times liquid. So they substitute for area instead of substituting for the length.
Oh, and then they just say that area is.
They substitute.
Mm-hmm.
Yeah, area is mass over density times length.
Sure. Yeah. Okay. Mass over density times length, and solve for that. And you can solve for L.
No, they just kept it as it is. So they just solved for L. They didn't solve for R in the beginning.
And we know mass and resistivity and all that.
Yeah, we know R is PL over A, and they substitute M equal density times length over length. I'm sorry.
Okay, yeah, they keep it. Yeah, I understand. They keep it as. I think the problem is not our algebra. I mean, sorry. The problem is our algebra. The problem is not our setup of the equation, because this is. Fine.
Yeah, I think we just messed up somewhere.
This is what we want. All right, L is equal to M over A. How is L equal to M? Wait a second. Mass over the area times the density. Yeah,
mass
sorry,
over
because this is this and this is the L.
Yeah.
So area times length is the volume, which makes sense. So we want L, which is that. So that's their first equation, and their second equation is just this. Yeah, which is just this. And rearrange that.
No, just a minute. Dang. Never had any problems rearranging equations like this before.
Yeah, right? I don't know why. Pi r squared rho.
Later can sometimes be wrong, so, like...
Yeah,
I think we had
understand.
too much campaign, that's why.
Pi r squared.
Since we know the gist of this problem, maybe we should just, like...
Yeah.
Derive it and then, like, go ahead.
Yeah, maybe get back to it tomorrow, maybe, or like never.
Yeah, get back to it later.
Okay, sure. Yeah, we do have we're solving this set of equations. I don't know why we're getting a different answer than later, but we're solving that set of equations, and that's the whole thing. Okay, let's take a look at one last question before we end it for today. So I won't quite mark 13 off, but I'll leave it underlined here. So 14 is our next one. So 14, suppose you wish to fabricate a uniform wire of mass M with metal with density rho and resistivity rho. If the wire is to have a resistance R and all the metal is to be used, what? Okay, so this is just it in general. The last problem in general. I think, right?
All right, we did it. Good job, guys.
Yeah. Pretty much if we solved the question before it, we solved this one. So I'll mark this one off. That's fine. So, yeah. Let's try 26 then.
26, 27, and 29 are really quick.
They're really quick? Okay.
Yeah, we can finish them in like 10 minutes.
Okay, then maybe let's try to do that.
26, you said?
The last three from the section.
Oh.
So 26 is the potential difference across a resting neuron in the human body is that many millivolts. And carries a current of about that many milliamps. How much power does the neuron release? Okay, that's not bad. P is V squared over R, which is not what we want, which is P equals. We just need VI. Sorry, we just need VI. That's all it is. So P equals VI. So voltage is 75 times 10 to the negative 3. And I is times 0.2 times 10 to the negative 3. So it's just going to be 75. 75 times 0.2 times 10 times 10 to the negative 6. So I get 1.5 times 10 to the negative 5 watts. Is that right for 26?
Yep, it is.
Okay, good. That's it. Just one equation.
15 microwatts. Damn.
Yes. Not too much. 27 is next here. So the cost of energy delivered to residences by electrical transmission varies that many kilowatt hours, that many dollars per kilowatt hour, through United States, that many dollars per kilowatt hour is the average value. At this average price, calculate the cost of leaving a 40-watt porch light on for 2 weeks while you're on vacation. Okay, so 40-watt light for 2 weeks. Well, we have to figure out how many hours that is. Let's figure it out. So in 2 weeks, I want to convert that to days, I guess, per week. So in 1 week, there's 7 days. And then, I guess I can just do this. I don't do it like this. I can just do it on my calculator. So 2 weeks. Each one has 7 days. Each one has 24 hours. That wasn't that hard. So 336 hours. And then to find the kilowatt hours, we just multiply kilowatts by hours. So 40 watts is how many kilowatts? Well, 0.04 kilowatts. Right? No, 0.40. No, 0.04 kilowatts. And we have 336 hours. So 0.04 times our answer is going to give us 13.44 kilowatt hours. And at the average price, which was $0.11 per kilowatt hour, what is the price? Just multiply this by 0.11. Per kWh is going to give me $1.47. $1.48. Okay. There's that. Hopefully that's right. Let's just check quickly. 27. Yep, that's good. B is making a piece of dark toast in 3 minutes with a that many watt toaster. So okay, so how many kilowatts is that? That's 0.97 kilowatts. And 3 minutes is how many hours? Well, it's just 3 minutes. So I want to convert that to hours. So how many hours in a minute? So in 1 hour there's 60 minutes. So 3 over 60.
It's 0.005. 0.05.
0.05, yeah, thank you. So that's how many hours. So now kilowatt hours, we just multiply that by 0.97. Oops, keep making 0.97. So I get 0.0485 kilowatt hours. And then we just multiply that by dollars per kilowatt hour, which was 0.11. So that's $0.005335, which is, yeah, that's right. Okay. Someone's got their mic on again.
Oh, sorry, my bad.
Okay, don't worry. So let's see part C. So drying a load of clothes in 40 minutes in a that many watt dryer. So okay, so 40 minutes is 2/3 of an hour. So that's right. Well, right, 0.67 hours, and it's a that many watt. So kilowatt is already what we want here. So 5.2 kilowatt thing. So multiply those two things together. 0.67 times 5.2 is our kilowatt hours. 3.484 kilowatt hours. And then just multiply that by 0.11, and I get $0.38324. So about 40 cents. Yep. Okay, that's
So
27.
don't leave a lamp or whatever they left on for a whole 2 weeks.
Exactly.
It's a bad idea.
You'll lose $1.48. But that's $1.48 gone nowhere.
Well, bad for the environment as well.
Yeah, that's true.
I guess.
That's true. Okay, let's try the final question from chapter 26.
Which is the same.
Which is the same as what?
Like the question that we did.
Oh, it's the same thing? Okay, yeah, so let's just finish it. So assuming the cost of energy from an electric company is that, compute the cost per day of operating a lamp that draws current of that many amps from that many volts. Okay, so, well, we need to find the amount of kilowatts that this does. So P equals VI, which is going to be 110 times 1.7. So that's going to be 110 times 1.7, which is 187 watts, or 0.1887 kilowatts. How many hours in a day? 24 hours. So 0.187 times 24 is 4.488 kilowatt hours. And then just multiply that by 0.11, which gives us $0.5. So 50 cents per day for this one here. Okay. So then there we go. We finished chapter 26. I think tomorrow the first thing we'll do is I'll try to figure out what's wrong with question 13, why we're doing question 13 wrong. So I don't know what. I'll figure that out for tomorrow. And then, yeah, so then that's all we have left is I'll just do that quickly. Hopefully spend less than 5 minutes on that. And then right away we're going to get into chapter 28 and chapter 29, which is the final 2 sections of the course. And we will hopefully finish that in the time tomorrow. There are quite a few questions in chapter 28. Let me count them quickly. 1, 2, 3, 4, 5, 6, 7. We have 24 questions in total to finish, which is quite a bit. That's a lot of questions to finish. So we'll see how far we get. We might have to start picking out questions. So maybe I'll do that for tomorrow. I'll just pick out some questions, and if we're running
When
out of
is
time,
the meeting tomorrow? Is it
5
same
o'clock.
time or is it
5
earlier?
o'clock.
Okay. 5 o'clock.
It's 5 o'clock. I hope that's what I put. Let's see.
All right. Good night, guys.
Have a good night. Have a good night. Yeah, 5 o'clock tomorrow. 5 o'clock tomorrow.
5 to 8.
5 to 9. Well, 5 to
9?
whenever we
Okay.
finish. Again, we'll take a break again at 6:30 and 8 o'clock tomorrow.
Sorry, Adam. Do you think we're gonna have like another small session before the exam, like from like 12 to like 2, like we did with CPS?
On
there?
Thursday?
Yeah.
It
Like,
depends.
just, like,
It depends.
touch
I
up on
don't know. It
topics we need.
depends on if we're gonna finish everything. I don't know. I'll have to decide tomorrow, I guess. What time is
Cool,
the exam
cool.
on Thursday?
3 to 5. 3 to 5.
3 to 5. I see. So maybe we'll see. We'll see how much egg we get done tomorrow. Okay.
Sounds good.
Goodbye. Good night.
Okay.
I
Bye.
would say
Good night.
didn't touch
So,
enough
Adam, can I
of
see
this.
27C real quick?
Would you like? Sorry. What? What was it?
Can I see 27C real quick?
27.
Like right before.
Here.
Right here?
Yeah.
Right there. Let me see that. Alright, thanks.
Good. Okay. I didn't really write much for these questions. Hopefully that makes sense.
If
Yeah.
we finish all
Have a
the
good night.
Have a good night.
practice questions,
Yeah.
could we do like stuff from like pre midterm stuff? Because
If we
didn't
yeah,
go
if we
right away
finish-
stuff. So we finish in time tomorrow, maybe before the because there's not as many questions on the exam for that
Yeah.
stuff. So maybe like I guess you could do the tutorial questions from some of the tutorials, or
Yeah. For like the earlier stuff, we definitely could do
you
that.
have like some select questions from standing waves and whatnot.
Yeah. If we have time though. So the main point though is to finish the practice for, this stuff, right? That's,
Yeah.
We gotta
The
finish. that.
magnetism one, I think magnetism will go a little quickly because it's not like as it's not as crazy as when we were doing the electric flux stuff.
Yeah,
where we
that's
were
true.
like-
It's a lot
I
of
don't-
just.
we were,
It's probably
like,
gonna be a lot of
couldn't figure it out.
directions. It's probably gonna be a lot of directions.
A lot of hands holding.
A lot of
the needle.
hand moving. Yeah.
I would love that. Holy.
So yeah.
My parents would be thinking I'm doing gang signs or something.
Yeah. That'll be us tomorrow. So yeah. Okay, I will stop recording.